Alright, this is going to be an energy problem example. Number 3 from practice. As always, you should be trying these problems for yourself at some point, so you have experience with how all of the different pieces fit together. So, let's take a look at the problem. It's going to be, I believe, right over here. Problem number 3, a 200-gram block is attached to a horizontal spring and executes simple harmonic motion with a period which is given, a quarter second, 0.250 seconds. The total energy of the system, E, is 2.00 joules. Alright, we're going to be trying to find two things here. One of them is the force constant K, and the other one is the amplitude of the motion. Alright, so we'll come back to my screen view. You can see I've written down some of the givens. It says it's horizontal, so we've got our spring attached to a mass. We're going to stretch it out some amount A and allow it to oscillate back and forth. So let's see, a couple of things we know for sure. Masses on springs, so omega would be the square root of K over M, and we can always prove that to ourselves again if we forget. Minus Kx is equal to MA, rearranging MA plus Kx equals 0, A plus K over Mx equals 0. If we're thinking about x as looking something like A cosine of omega t plus A phase, then the amplitude, sorry, not the amplitude, the acceleration would look like minus A omega squared cosine omega t plus phase, which will give us basically minus omega squared plus K over M is equal to 0, so omega is square root of K over M. Now I did run through that pretty quickly. Double derivative of a cosine isn't that hard to do in your head, but the rearranging and substituting in, I did skip a couple steps. Alright, why do I want that? Well, omega is also equal to 2 pi divided by the period. So now I know 2 pi divided by period is the square root of K over M. And since I'm given T and M, that means I actually have enough information to find the answer in part A. So I'll have to square both sides to get things out from under the square root. And 4 pi squared over T squared times the mass would give us K. Now we do need to be careful about units here. If we want the units to be normal units like Newton per meter, for K, then we need to convert mass into kilograms, so 0.200 kg. Alright. I suppose I can just do 2 times pi divided by, the period was 0.25, and then square it. Multiplied by the 0.2 for the mass. K should be 126.3 newtons per meter. You would probably report that as 126 newtons per meter. However, I do want to keep that extra digit in case I might want it for part B. I'm not actually sure yet. Alright, so I don't really want to run through the whole proof for total energy right here because I just did it not that long ago in the previous video. But it's the kinetic energy plus the potential energy, and those would look like, let's see, kinetic energy is 1/2 mv squared, where v is going to look like minus A omega sine omega t plus phase, and we'll have to square the whole thing, and the potential would look like, I'm hating my u back here, oops. And the potential would look like 1/2 kx squared, so we'd have an A squared cosine squared omega t plus phase. Alright. Of course, we can take advantage of how omega is defined, so since this is going to give us omega squared, and omega squared is K over M, that means we actually have common factors And since we have common factors, the 1/2 Ka squared can be factored out in front, and it leaves the sine squared plus cosine squared, which is equal to 1, by a nice trig definition, or trig theorem. So we know that the total energy looks like 1/2 Ka squared. We're given, oops, forgot to square the A. So we're given E, and we know how to find the K. So 2E over K, take the square root, will give us A. If we went to do this in pure variable form, it would be 2E over 4 pi squared times T squared, and an M also on the bottom. You can handle it whichever way you want. If you're using the K, make sure you keep that extra digit, and that should do it. I'm actually going to do it the long way just for fun. So that would be 0.25 divided by 2 pi, because I'll take that stuff out in front of the square root. Then I'll multiply that by the square root of the energy, which is 2 times 2, divided by 0.2, which is the mass. And I get 0.178 meter. Doing it the other way, square root of 2 times the energy is 2 joules, divided by 126.3, and it gives the same answer, so we're definitely good there. Alright. That is an example of using energy. In the homework, the use of energy gets a bit more interesting. You have to flip back and forth between the two definitions. So you want to find everything in terms of E, but you may have information in terms of A. So ratios might be an appropriate way of thinking about this. Also, if you happen to know values for things, that's another way of dealing with it. And I believe in the homework problem it also talks about at a moment when the kinetic energy is equal to twice the potential energy, or possibly vice versa. If that was true, then you'd have to write the total energy is 2 times the potential plus the potential, where this is your kinetic energy represented in terms of potential. Or you could do vice versa. And you could say, well, if the kinetic is twice the potential, then the potential is half the kinetic. Okay, so those should help you out with the problem on the homework, at least a little bit. And I think that will be the end of this video. Alright. Doesn't actually stop until I click yes.